Dickson. He's an Aerospace Engineering Masters student in the Cognitive Engineering Center at Georgia Tech, Pathways Intern at NASA Kennedy Space Center, and will also be joining UNSW soon as a PhD student. So, great.
All right, thanks for that introduction, Andrew. When I was invited to give a talk here, I currently work at SwampWorks. I work on projects, additive construction, and ISRU. And when I was asked to give a talk here, my first thought was, wouldn't it be nice to give a talk on technology roadmaps, how we use them and how they're useful towards our goals. And one of our goals that we're going to see more of in this forum is mineral mining of asteroids, and more generically for extreme environments in space. And a lot of things are going to have to be built in order for that to be a viable enterprise. One of which is having a viable technology roadmap. So what do I mean when I say a technology roadmap? One of the examples of that is what I consider to be the gold standard for space technology roadmaps. Currently, the 2015 NASA Technology Roadmap. And if you never sat down on the beach and getting that a good, breezy read in the sun, I recommend it. It's a good refresher for those who already know about technology and want to know about the latest developments that are going to need to be happening over the next decade and a half. But it's also a good inspiration for someone who's new to space mining and wants to learn more about it. Now, what a technology roadmap generally does is it connects the policy, the needed mission capability, to the funding, the strategic investment plan. And this technology roadmap accomplishes this thinking by laying out a schedule and deliverables for technology capabilities, both new and already existing, but that need to be improved. There are 15 categories in the NASA technology roadmap. But the big question here, relevant here, is how does it address asteroid mining technology needs? You can probably guess the answer. Currently, it doesn't, not explicitly. And the reason for this is, well, the input to that technology roadmap, which is NASA's strategy, NASA policy. I want to verbatim lay out the 3 strategic objectives of NASA that determine our technology roadmap. Expanding the frontiers of knowledge, capability, and opportunity in space, advancing understanding of Earth and developing technologies to improve our quality of life, and serving the American public and accomplishing our mission by managing our people, technical capabilities, and infrastructure. I would say the second of those objectives comes closest to asteroid mining. But in NASA strategy, it is referred to in the context of commercial ventures. In other words, it's regarded as a strategic objective that will be set and pursued in the private sector. So that means, essentially, we have to modify and modulate the technology roadmap we have, the NASA technology roadmap in this case, and compile other technology roadmaps, both terrestrial mining and roadmaps that indicate asteroid mining, and that's what I tried to do here, is compile what the needs are for asteroid mining and perhaps get a modified technology roadmap for asteroid mining specifically. The good news is a lot of the technology needs for space mining and NASA policy in general do coincide. Same enabling technologies further both NASA's strategic objectives and those of potential asteroid mining, particularly in all these areas: in-space propulsion, robotics, ISRU in particular. So the question is, what do we need to modify? So that's what I took upon myself for this talk. So the area of the technology roadmap, NASA technology roadmap, that comes closest to addressing asteroid mining, there's 3 of them: prospecting, resource acquisition, processing, and production. And you can see the numbers in which they're located in the technology roadmap. So for brevity, I'm just going to focus on prospecting. reconnaissance, prospecting, and mapping that first of those three categories. So here's some sub-areas of prospecting that are cited as technology advancement candidates. Notice a pattern here. We're talking about equipment for drilling, penetrometers, flow instruments, sensors, all very good things. We need to advance those things in order to accomplish our goals. There's something missing here, though. I noticed that once I started doing research into general terrestrial mining technology roadmaps, new exploration methods, novel exploration methods. In the Space Resources Roundtable and in this forum, you hear people talk about these, and you don't see them reflected currently in the prospecting portion of the technology roadmap. Both methods applicable to space mining and methods being developed for terrestrial mining. So what I did is there's a couple of sources I went through here. This is the Asteroid Mining Technology Roadmap and Applications Final Report from International Space University in 2010. The closest thing you'll find to explicitly, here's an asteroid mining technology roadmap, but it's much more general than that. I wanted to get more specific into the technology. I also looked into a general technology roadmap for mining in particular. This is from ISRU Futures, roadmap for unlocking future growth opportunities for Australia in mining. And one thing I noticed is, especially in the latter report, there are three major areas that are ripe for major game-changing advancements in the prospecting area. Specifically, exploration undercover, data-driven mining, and robotics and automation. Before I go into those, I want to frame the Prom and mission form. So in the ASTRO report, this more specifies what we mean when we say asteroid mining. They made recommendations for the architecture of the first attempted asteroid mining mission. Their specific recommendation was a short-term, fully autonomous, large asteroid mining mission described, and you can read this in the report itself on page 30. They did a trade study, and some of their reasoning was a little bit subjective, but that was the architecture they recommended for a first trial asteroid mining mission. And the key phrase there, I think, is fully autonomous. So, and that by fully autonomous, we know it's going to be supervised by humans, possibly humans in space, but humans are not going to be physically on the asteroid. So for that mission, here are some of the technology advancements that I thought were relevant, comparing the METS report on Australian mining and basically terrestrial mining needs that could be modified for space. So what they specified specifically for exploration undercover was, these are some of the technology advancements that are going to happen here on Earth in the next 10 to 15 years. Directional drilling, first principles ore body formation modeling, 3D seismic exploration, deposit modeling that builds on existing characterization data sets, and 4D geodynamic maps. So how can we modify those for space to put in our space asteroid mining technology roadmap? Well, there's a lot we can modify. Going through the Space Resources Roundtable, you see people suggest things like adaptation for low gravity, right off the bat, anchoring your mining equipment in low gravity environments. Adaptation for icy rock, regolith, low temperatures. There are temperature extremes, as we know, in space mining that necessitate a lot of modification of these technology needs. Well, what I do? There we go. Surface gravimetric surveying, shock heating and freezing, and a whole lot more. So of the three prospecting areas, I thought this was the most ripe for adaptation of terrestrial mining methods. And so you can see, we would mostly manifest that in modifying the prospecting portion of the NASA technology roadmap. So that's that area. As far as data mining goes, the good news is the NASA technology roadmap actually has a lot of parallels with terrestrial mining technology roadmaps. So terrestrial technology needs are integrated sensors, sensor durability, embedded sensors, advanced user interfaces, improved mathematical models, of course cybersecurity. There's not much adaptation that needs to be done in this area, other than radiation and low temperature hardening of sensors for space applications. And one thing I thought would be a good adaptation, though, would be exploration studies to feed data sets similar to parallel work done for Mars data-driven prospecting, which Laurent actually presented at the latest Space Resources Roundtable. Basically, and these are the areas that would be modified in the NASA 2015 technology roadmap to get to that. As far as robotics and automation goes, I was a little disappointed that the symbol in the METS report was not a razor. Razor-shaped razor being the robot that Rob mentioned in his last presentation, but that was a little bit of a joke. But the terrestrial roadmap needs machine vision, advanced materials, additive manufacturing, and swarm robotics, and you see this, and not much modification needed other than radiation hardening, low temperature hardening. One possible addition is self-replicating robotics. We don't see this in either terrestrial technology roadmaps or NASA technology roadmaps, and there may be political reasons for that. I'm not sure. But yes, I recommend an entirely new section to the NASA technology roadmap to reflect this. By the way, that self-replicating system was proposed by Rob and Phil Metzger at the 2012 Space Resources Roundtable. So this is just kind of a taster of the research, investigation, and lit review I hope to do in my PhD work for developing the adaptation of terrestrial mining methods for asteroid mining in particular, or perhaps other low gravity extraterrestrial environments. Who are the customers for this kind of technology roadmap? Space agencies, companies, professional organizations, anyone with an acute interest in reducing the long-term cost of investment of off-Earth mining, particularly of asteroids. The takeaway I want you to take from this is there's a lot of parallels of space mining needs with terrestrial mining technology needs, and using some of those cutting-edge technologies modified for space may be the key input that we need for industry partners to plan their technology investments for the coming space gold rush. I'm going to leave you with a quote from the ASTRA report. As referring to space asteroid mining, as this venture would likely require significant levels of investment for startup and research and development costs, the project is not currently financially viable. The most influential driver is the mass return ratio. In order to come closer to making asteroid mining a financially viable venture, we strongly recommend that engineering efforts be focused on maximizing the mass return ratio, specifically ISRU. So this should give us a glaring indication of the importance of developing certain technology to entice investors into making off-Earth mining a reality. Thank you very much.
Okay, one question, then we can go have a cup of coffee.
I've got a quick one. Mass return ratio, how's that bringing it back?
That is the ratio of the mass that you're bringing back to Earth versus the mass that you brought there. So that can be drastically increased by propellant ISRU, in-situ processing, propellant ISRU, in-situ processing, and additive construction of structures at the place in question. This tends not to be something that's really considered in public consideration of off-Earth mining, and I think it needs to be.
Okay, quick one, Mark.
30 years ago, Professor Lewis of University of Arizona said we should have a minimum mass return ratio target of 100 to 1.
Yeah, those are, the top number you see there is 3. The ASRU report, I don't think, it was much more of a legal and policy document than a technology document per se. So I think if we had a more thorough investigation that ran numbers like that and illustrated what we need to do to get to that number of 100 to 1, then that would also be a good input for a technology roadmap.
It in fact becomes a design driver.
Sorry, what was that?
It in fact becomes a design driver.
Exactly, I totally agree.
All right, thank you. Can we thank David and this morning's speakers?